With respect to learning outcomes of this lecture, we want you to be, firstly, familiar with what is a software architecture and understand fundamental concepts behind software architectures. We also want to explain how architecture relates to the other aspects of software engineering, such as requirements, the software process, analysis, and design. We want you to be familiar with designing a software architecture. So in this lecture, we'll show you a technique called attribute-driven design for designing architectures using standard architectural tactics. We also want you to be familiar with analyzing an already designed software architecture. So we will explain that. And finally, we will introduce you to a couple of technology architectural frameworks. We begin by explaining what a software architecture is. So what is architecture? Architecture is an externally visible component, its structure, property, or its relationship with other externally visible components. So why do we make this notion of externally visible important? It is so that you can reason about how the system meets its requirements. In order to reason about a system, you have to look at things that are visible about it. Okay, certainly, and by the way, what do we mean by requirements? Certainly functional requirements, but more importantly, architecture is what determines how or whether a system meets non-functional requirements. Informally, you can think of architecture as the things that matter to the system, or the things that are hard to change about the system. So when it comes to software architecture, all that means is that the components, properties, and relationships are software components, software properties, and software relationships. The goal of a software architecture is obviously to meet the requirements of the system. As we know well, there are two kinds of requirements, functional and non-functional. Functional requirements are specified by the use cases, so the software architecture has to implement the use cases. In other words, the architecture must support the use cases. Then the architecture has to meet non-functional requirements. Most non-functional requirements will fall under the standard categories of modifiability and scalability, performance, security, testability, and usability. Note that these non-functional requirements will have to be quantified or made measurable before you can properly implement them. Once these non-functional requirements are quantified, the terms that they are quantified in are also known as quality attributes. For example, performance is quantified using the term response time, and therefore response time becomes a quality attribute. A useful question to ask is, how is architecture different from design? Because both of these activities have to do with the how of the system as opposed to the what. So both architecture and design are indeed about the how of system building. However, architecture consists of those design elements that A, apply to most, if not all, of the system. For example, the choice of the programming language. B, are hard to change once they are in place. And C, are the design decisions which are essential to meeting the functional and non-functional, and in particular the non-functional requirements of the system. Below are some of the tie-ins between architecture and the rest of software engineering. With respect to requirements, requirements obviously define what the right architecture should be. In other words, requirements drive the architecture. Let's take project management. For example, when you have agile processes, you cannot go into your tight iterations without having the architecture defined. Secondly, teams are often organized around architecture. So if architecture is the components within your system, then typically teams are organized around these components. Also, the elaboration stage, if you remember, is where the architecture is designed in detail and also validated. Let's take testing. The architecture must be tested to ensure that it meets non-functional requirements, and so on. Next, we cover some concepts in software architecture. Architectures of large systems are so complex that they need to be described using multiple views. In other words, you can't just give one explanation or one description of an architecture with, say, one picture and expect people to understand it. Each view might focus on some aspect of the system and be of relevance to a particular set of stakeholders. For example, the software development teams might be interested in the separate components of the architecture, so that each component team can be responsible for its piece. the software development team might also be interested in how files are allocated to directories because they might want to build the system. And that is another view. The business sponsor may be interested in the development costs of each component of the architecture, so might want to see some kind of bill of materials view of how much the system costs. Architectural views are many. However, we can cluster the views into types of views. These types are described below. Module views show the functional decomposition of the system into different modules. Module views that show subsystems are often important for new engineers coming onto the project so that they can see how the various pieces of the system fit together. Module views that show the software build structure are also useful for developers. Any class or object UML diagram used to show how software classes or objects relate to each other is in fact a module view. Component and connector views show you how different components connect to each other. For example, you might want to show how the various technology components connect to each other in terms of their networking. The figures in Lecture 1 titled A Conceptual View, Business Process View of an Enterprise System, the three-tier view of an app, complexities in an enterprise system are all component and connector views. Any UML sequence diagram, and in fact any UML diagram intended to show dynamic behavior, is a component and connector view. Allocation views show you how the software implementation should be deployed and allocated to hardware, for example. An allocation view that shows how these system components are deployed on the target hardware would be important to, say, system administrators. A UML deployment diagram is an allocation view. Multiple stakeholders will jointly specify the functional and non-functional requirements based on what is important to them. For example, the business sponsor might specify cost, a representative or surrogate user may specify performance, and so on. After the architecture has been designed, the stakeholders will want to examine and analyze the architecture from their point of view. Usually, enterprise architectures are so complicated that you can't show everything in one view. This is why multiple views are necessary.
Another way to look at architectural views is to try and understand what all views are necessary in order to describe an architecture. So Philippe Crucian from Rational Software Corporation came up with this 4+1 view model of software architecture. Basically said you need these 5 views to properly describe a software architecture. So in the middle is the use case view. So these are, which describes the functionality the architecture has to implement. Starting from the top left, the next view is the logical view, which describes the conceptual components of the architecture, as well as how that functionality might be implemented in that architecture at a conceptual level. So not at an implementation level, but at a conceptual level. So maybe you can think of your solution analysis diagram as something that belongs in the logical view. To the right of it is the development view. So this is how the system may be looked at from a programmer's perspective, and it's concerned with software management. This view is sometimes also known as the implementation view. Here you might talk about describing how the program files, the files with the code are how the code is broken up into files and stored on the file system. How you might build the system, how you might check out the system from SVN, things like that. Going down from there is the physical view, which talks about how the software components are mapped to the hardware, to the network, to servers, and so on. And to the left is the process view, which deals with the dynamic aspects of the system, explains the system processes and how they communicate, focusing on the runtime behavior of the system. In a complex system, this view is needed because you need to understand things like concurrency, distribution, how things are integrated, performance, scalability, things like that. So the last thing you should think about is how this 4+1 view relates to the architectural slides of the previous architecture styles of the previous slides. So essentially, you can use a variety of architectural view styles in each of these views. And one of the things you need to be thinking about in this class and also in the project is what diagrams or architectural styles you will use to represent each of these 5 views.
Architectures are built using a combination of architectural tactics. In the next few slides, we will discuss these tactics.
So let's talk about tactics for implementing quality attributes. Let's begin with availability tactics and then go through the list of all the other kinds of non-functional requirements. So for availability, you can categorize tactics into 3 categories. One for detecting faults, the second for recovery, and the third for prevention. So with respect to detecting faults, you basically have 3 approaches. One is that the component that is being managed periodically pings you and tells you, the manager of the component that needs to be available is periodically pinged by the manager to see if it's up. The second way is for the component that is being managed, the component that needs to be available, for it to periodically send a manager a heartbeat, a message basically saying that it is up and running. And the third approach is to do some kind of an exception mechanism. So you don't have to periodically ping the component, or you don't have it send you a message periodically, but rather if it dies, if something happens, an exception is raised and a message is sent to you at that time. Basically, the third one is a more efficient way of making sure that a manager is notified if the component that needs to be available goes down. The second category is for recovery, tactics for recovery. So with respect to availability, the usual tactic is some kind of redundancy. So having 2 database servers, or 2 web servers, or multiple web servers that you route requests to in some kind of manner. Or simply, if the system goes down, reboot it. By the way, redundancy can be active or passive. So you can have 2 databases that are both up at the same time, and every transaction is reflected in both databases. Or it could be passive, which is that only one database is actually getting updated. But if the system goes down, that database is transferred over to a second one and then brought back up as a replacement. The third category of availability tactics is for prevention. So one way of making sure a system is available and is doing the correct things is by using transactions. You would have seen transactions described in your database class. And another tactic for availability is demand management, which is prevent things like denial of service attacks, or prevent the system from being overloaded by only allowing a certain number of requests to go in at any given time. Looking at modifiability tactics, the general principle is the more you're able to localize and keep modular, the more you're able to modify later. So for example, if a search algorithm is localized into a particular class, well, then you can modify that search algorithm by simply modifying the class. Similarly, if all the data access related functionality is localized in a database, then by simply replicating the database, you can get scalability. The whole idea here with respect to modifiability is that you want to reduce coupling, which is the knowledge a component has with respect to another. Basically, any private knowledge that one component has of another component will reduce your ability to modify either of the components or to replicate either of the components. And increase cohesion, which is the dual of coupling, which is the opposite of coupling. The idea is that each component does one thing well, And if you want to improve that one thing, or if you want to have multiple of that one thing in order to scale it, you can do so. The third category, the third kinds of tactics are for performance. And for performance, you essentially have the following tactics. You can either do things more efficiently, essentially reduce resource usage. You can reduce switching because switching has costs. You can simply add more resources, add more memory, add more, buy a bigger machine with more horsepower. Or you can do things in parallel. And just like with availability, another way of improving performance is by controlling demand, so that at least those requests that are in the pipeline of being processed, at least those will have good performance. You will see that the tactics for security are very similar to the tactics for availability. Now, these can be categorized into three kinds of tactics: for detection, resistance, and recovery. So with respect to detection, standard ways of implementing that are by monitoring access patterns and comparing them over time. So when you see anomalous access patterns, then you begin to suspect a security breach. You can do this in real time, or you can store large amounts of data and analyze it offline to figure out whether you've had a security breach in the past. The second category of tactics is around resistance. So basically prevention of security breaches. And the way you might do that, one is through authentication. So you have to log in or authenticate yourself before you have access. You have levels of authorization, so not everybody is allowed to do everything, so that exposure is limited by limiting access. Another tactic is encryption, basically protecting the data so that not everybody can read it, or rather an unauthorized person cannot read it even if they had access to it. And the last kind of tactic is through integrity preservation techniques. Things like checksums or parity bits. You might have seen this in your communication course to make sure that a packet has been has been received correctly. Things like that. The last set of tactics are basically recovery tactics. So all the availability tactics apply here, basically around redundancy. And the other tactic used here is using audit trails. So to basically identify who did what and when, so that potentially you can even roll back to get rid of a security problem. And also you have a trail that you can then use for investigation. So for identification of the problem first, and then investigation of the problem. What was done, who did it, and so on. So now let's take a look at testability tactics. Remember that the goal of testability is the goal of testing, which is to show the presence of faults and not the absence of them, because that that's not possible. So here are some tactics for implementing testability. One is being able to record all transactions that the system does and then be able to play them back. So many systems will use logs to output everything that the system does, and some systems will allow you to basically replay the log to make the system do exactly what it did earlier, just repeat what it did earlier by redoing what is there in the logs. Another testability tactic is stubbing out the interface from an implementation. So you can test everything around a component by simply accessing its interface while that component is under development. And the other way too, so if you're testing a component that requires another external component to be able to test it with, and that component is not available, then you can create a stub for that component and then test your main component, the component that you're building right now, against the stub of the other component. In many systems that access external services, so suppose you're building a PayPal-like system that charges your credit card and so on. In order to test PayPal, you can't start accessing credit cards during your testing process, because that would debit cards without purchases being actually made. So the idea here would be to create a stub of the credit card interface and link that into your PayPal system, so that you could simulate credit card payments being made without them being actually made. This idea is similar to the next one, which is this notion of specialized testing interface. But if those of you who have used JUnit will understand what I mean by specialized testing interface. So the idea here is to create a test harness that tests a component in all the ways that need to be tested. So it's not a complete application; it's just a small piece of an application that tests the component thoroughly. And the final way is to use internal monitoring. So have enough logging within your system, have enough notifications within your system that you will be notified if something fails and what were the actions leading up to that failure, so that you can then figure out what went wrong and go back and fix it. So now let's talk about tactics for implementing other quality attributes. So let's start with usability. So tactics for implementing usability are, of two kinds. You can think of runtime usability tactics and design time usability tactics. With respect to runtime usability tactics, it is things like giving feedback to the user. So for example, when you save a file, and if the file is a large file, then putting up an hourglass or a progress bar to show that things are going on and that the system is not hung is a usability tactic that falls under the category of feedback. The other runtime usability tactic that human computer interface designers use are what are known as task models, user models, and system models. So they basically build these models of tasks and users and systems and use these models to understand how users will interact with the system. Try to figure out how they might best interact with the system in the quickest, most efficient way with the least number of clicks to achieve what they need to achieve. And they use these models to then design the system. There's also a tactic for design time usability, which is basically separating the UI into a separate set of components so that you can modify the user interface without changing anything with respect to the functionality, without changing the services that the system is supposed to provide.
We now go on to how we might design software architectures using the concepts and tactics we described earlier.
So here's how you go about designing the architecture for a system. You essentially use a recursive decomposition process. So to begin with, start with a single module which represents the system. Essentially, you're beginning where solution analysis left off. Create a prioritization of the architecturally relevant requirements. In other words, those functional and non-functional requirements that will have the most impact on the architecture. So you basically want to look at the most complex use cases and the most complex non-functional requirements. By the way, you will find that the non-functional requirements are the ones that have most impact on the architecture. Start with the first most important requirement. Design the architecture using what are known as architectural tactics. You will see these architectural tactics in subsequent slides. Then take the next requirement and apply that towards designing the architecture, and the next one, and the next one, and so on. At some point, you will find that you need to break the system up into smaller modules with well-defined interfaces. So do that. And then once you have, at each step, at each iteration of this architecture design, verify the architecture using the use cases which define the functional requirements, and enhanced with quality scenarios. So not just use cases that describe what the system is supposed to do, but use cases that describe what the system is supposed to do plus how it is supposed to do it. So you should be able to log in, which is a functional requirement, within 5 seconds, which is a non-functional requirement. And as you design this architecture, document this design using views. 4+1 views, and the diagrams that you will use there will be the diagrams corresponding to the different architectural view styles: module, component, connector, and so on.
As you design the architecture, your designs have to be captured in work products. We have listed some standard architecture work products. Two of these work products directly correspond to the 4+1 views as follows. The subsystem model is the same as the logical view. The target environment is the same as the physical view, or at least one component of the physical view, which is the deployment part of the physical aspects of the system. The other views may be captured in the system architecture work product. In other words, in your system architecture work product include development views as well as process views. Note that the use cases have already been captured as requirements. So what use cases and scenarios do you capture as architectural work products if you plan to conform to the 4+1 view requirement? Basically, you identify, so you don't duplicate, but you identify the architecturally important use cases and scenarios here.
An important process with respect to architecture is analyzing and validating architecture. So you might analyze or validate an architecture that you have designed, or you might analyze and validate an architecture that you have not designed. So for example, say a vendor comes to you with a certain system, you might want to analyze and validate its architecture. Or if you're buying a off-the-shelf product, you might want to analyze and validate its architecture before you put it to use. The techniques for all of these are common, and we will look at these techniques next.
The techniques we will show you were designed at the Software Engineering Institute and form a body of best practices, and are collectively called the ATAM, or the Architecture Trade-off Analysis Method. Basically, the goals behind analyzing architecture is to figure out if this architecture is suitable for the system being built or acquired. That is, to answer the following questions. Will the system meet its functional goals? Will the system meet its quality goals? So for example, will it meet performance goals? Can it be modified in the ways planned? Will it be protected under specific threats? And also to identify, even if it does meet those goals, what are the risks in this architecture? Step one of the ATAM is to present the architecture, make a presentation about the architecture and explain how it meets the functional and non-functional requirements. This step is done by whoever designed the system. It could be you if you designed the system, or it could be a vendor who is trying to sell you the system. The next step, step two, is to create real-world scenarios specific to the system that will be used for validating the architecture against its quality attributes. For example, all systems submit a vacation request the day before Thanksgiving. Will response time be within the prescribed limit of 5 seconds? So how do you create good scenarios? To begin with, you have to clearly identify the quality attributes like response time, like mean time between failure if it's an availability requirement, etc., that the scenario will test. Then cover a range of anticipated uses, normal uses. Basically your use cases will tell you that. Then test anticipated changes to the volume of uses of the system, so growth scenarios. Then cover a range of unanticipated stresses, what we call exploratory scenarios to the system. A good scenario will make clear the stimulus or event, like Thanksgiving or Mother's Day, that will initiate the scenario, and what system responses, once again, what quality attributes and their range of values are of interest. By the way, where have you seen this before? You've seen this in acceptance tests. It's the same thing. So here are some example scenarios. First, we'll take a functional or normal scenario. A remote user requests a database report via the web during a peak period and needs to receive it within 5 seconds. Let's talk about a growth scenario. Add a new data server to try and reduce latency in scenario 1, which is the remote user requesting a database report, to 2.5 seconds, and this data server should be brought up within 1 person week. Thirdly, let's look at an exploratory scenario. Half the servers go down during normal operation. System availability should not be affected. Basically, scenarios should be as specific as possible.
A quick way of defining and documenting scenarios is by using what is known as a utility tree. So on the left, the utility tree is rooted at a node called utility. The first level of children are the standard categories of non-functional requirements or quality attributes. Performance, modifiability, availability, usability, security, testability, and so on. At the next level are basically categorizations of these further refinements of these categories. So, for example, with respect to performance, this particular system had two categories of performance. One was data latency, the other was transaction throughput. With respect to modifiability, you had new product categories or the change of a off-the-shelf system purchased for use within that system, things like that. And at the leaf of this utility tree are the actual scenarios, labeled with a prioritization. Once again, the prioritization being a two-component prioritization. The first component standing for importance, for criticality, and the second component standing for perhaps urgency. So when this architectural evaluation is done based on scenarios, these scenarios start bringing out questions that help analyze or validate the architecture at a deeper level. So if it's a performance scenario that is described, then the architect then explains how the architecture meets that scenario. The folks evaluating or analyzing the architecture can ask deeper questions. So when it comes to performance, they can say, so how are priorities assigned to processes? If the architect responds with, well, I have multiple processes that deal with these requests. The evaluator can ask, what are the message arrival rates? What are the expected transaction processing times? With respect to modifiability, the evaluator can ask, are there any places where the layers are broken? Is there any coupling between components? What components are connected not synchronously but asynchronously? So that there's actually more of an opportunity to be able to modify something or do some kind of delayed binding to that component. Things like that.
Here a scenario is being used to probe an architecture to see how it does or does not support the scenario. In this case, the question asked is, how does the system recover from the hardware failure of the main switch? And the architecture responds with, for example, there are two switches, each with its own CPU and each running a different operating system. The backup switch has a watchdog that receives periodic heartbeats from the main switch. If the backup switch does not receive a heartbeat, it will take over by shutting down the main switch and switching operations over to itself.
So the goal of this architectural evaluation or architecture analysis is, of course, to see how or whether the architecture meets the important functional and non-functional requirements. But it actually goes more than that. You want to understand also how the architecture, to what level the architecture meets the functional and non-functional requirements. So the idea is to basically identify in the architecture three kinds of things: sensitivity points, trade-off points, and risk points. So sensitivity points are the components of the architecture that are important to meeting a particular set of requirements. So what component or what property of the component enables the architecture to meet a requirement, that is known as a sensitivity point. So for example, a backup database is the sensitivity point for reliability or availability. The degree of encryption is the sensitivity point with respect to security. Things like that. The second kind of items that you want to bring out through this architectural analysis are what are known as trade-off points. A trade-off point is a property or a component that affects more than one quality attribute. And in one case, it affects it positively. In one case, it affects it negatively. Okay. And finally, a risk point are those sensitivity or trade-off points which are close to the limit. So in case the load on the system increases beyond a certain amount, or the number of the number of users increases, whatever it might be, that component of the architecture is likely to be stressed beyond being able to meet its requirements. Those components or properties are known as risk points.
In almost all cases, when you build a new system at least, you will develop your system on a framework such as Enterprise Java or J2EE, for example, the Mozilla suite of products, or the Android framework. So we have to understand what architecture, design, and analysis means in the context of these frameworks. Frameworks provide an architectural foundation for your system or application. This is because they provide architectural templates that you then customize for the various aspects of your application. Basically, for several of your standard functional and non-functional requirements, the architectural decisions will be made for you by the framework. In other words, frameworks predetermine many of the sensitivity, trade-off, and risk points of your system. One very useful technology framework is Eclipse. It provides the base functionality to be able to build what are known as integrated development environments for various things. We used Eclipse to build the EcoFlow integrated development environment. We won't go into Eclipse here. You can learn more about this in the EcoFlow lecture on architecture. Three common technology frameworks are mentioned in this slide. For A, Enterprise Java for building multi-tier enterprise applications. B, the Mozilla framework that helps you build the front-end portions of web-based applications. And C, the Android framework for building mobile applications for devices that run the Android OS. And finally, we reprise what we have learned. The learning outcomes of this course were A, be familiar with what is a software architecture and how architecture relates to the other aspects of software engineering, such as requirements, the software process, analysis and design, and also to give you some concepts or behind software architecture. To this end, we defined software architecture and presented some concepts with respect to architecture, such as views and quality attributes. The second learning outcome was to be familiar with designing a software architecture. We showed you a technique called attribute-driven design for designing architectures using standard architectural tactics. We also wanted you to be familiar with analyzing an already designed software architecture. For this, we presented the Architecture Trade-off Analysis Method, or ATAM. And finally, we explained what technology architecture frameworks were, how you use them, and gave you a few examples.